Okay, good morning and welcome to the second week of PITP. I hope all of you had a good weekend. You may have heard that there was severe flooding in this area. So I just want to emphasize being extremely careful. And as you know, there are sudden downpours, so please stay away from high water and things like that. Stay safe. Okay. On a positive note, we have Grisha back to tell us the second installment of his lectures on the MRG and applications to one-dimensional spin chains and gauge theory.
All right, thank you. Okay, so today we're gonna basically talk about the Schwinger model in 1+1 dimension. And the main message of the today lecture is to how to put it on a lattice. And then at the end, I'll explain how to apply density matrix renormalization group to this lattice lattice version of the Schwinger model. So the short plan of today's lecture is the Schwinger model. Hamiltonian approach. Staggered fermions. And well, density matrix. Group to the model. All right, so let me start with the Schwinger model. One plus one dimension. So the Lagrangian of the model is electromagnetic field term plus Dirac field term. Right. And so it's in 1+1. So we have two component fermions and gamma matrices. So we choose gamma matrices in this form. Where Minkowski metric is +1, -1. All right, so now we would like to define Hamiltonian for this model, and let's for a moment work just for convenience work in d+1 dimension. So we have to define canonical momenta. So P mu would be the variation of the Lagrangian over 0 A mu. So canonical momentum for the gauge field is F0. And for Dirac field, will be epsilon bar 0. And from here, we immediately see that, well, this is standard stuff. So P0 is 0, so it's called primary constraint. All right. Right, so the Hamiltonian is, we obtain Hamiltonian through Legendre transform, so it's going to be P mu pi 0, plus and so can compute, so it's this is the electromagnetic part, and all right, so finally, so we can finally we can simplify this a little bit, and then we're going to get expression. Sorry, I also forgot there's also zero part here. So using that canonical momentum pi is f0, we can write this as in this form. So going to be 1/2 pi plus 1/4 j. There will be the Dirac term this, and there will be term which is minus a0 minus right. So at this we have a primary constraint according to Dirac, and the primary constraint has to be constant in time. So if we apply the equations of motion in the Hamiltonian form for the primary constraint, this will give us the secondary constraint, so it has to be 0. And this gives me the secondary constraint, which is divergence of canonical momenta equals psi bar gamma 0 psi. And this is secondary constraint. But we know how it has a different name. It's a Gauss law. Right? Any questions so far? All right, so let's go back to 2 dimensions, and let's choose a temporal gauge. Temporal gauge, meaning that we set a0 to 0. Then we get the Hamiltonian for Schwinger model, so this term Fij is not present, and also P1 in the Schwinger model is which is F0 F1 0. It's a minus time derivative of field A1, and this is electric field. So we can write the Schwinger Hamiltonian as the integral over line 1/2 electric field square. So electric field is a canonical momentum in this case, plus psi bar minus I gamma 1 x plus gamma 1 plus m. So this is the Hamiltonian for the Schwinger model with the Gauss law constraint, which is dx electric field x equals charge, density of charge psi bar. At this point, this electric field is an operator, so we have canonical commutation relations between electric field in this case and the gauge field. So it's minus I delta x minus y. And there's also canonical commutation relations between psi bar and psi, or psi and psi dagger. So I can write this as anti-commutator of psi alpha pi psi beta is I delta x minus y, which means that anti-commutator of psi alpha x, psi dagger beta is just delta alpha beta delta x minus 1. All right, so at this moment, so we formulated Hamiltonian for the Schwinger model, and we're ready to start putting the CD on the lattice. All right, so first of all, yeah, so let's first consider only pure fermions. Fermions only. And we know that we have, for the fermions, we have a Dirac equation, which in the Hamiltonian formalism is just like a Schrodinger equation. So it's I psi dot commutator of psi with h. And this gives us equation for psi. So we'll write it first. Psi dot equals minus I gamma 0 gamma 1 dx psi and plus gamma 0 m psi. So this is just a Dirac equation, and I can write it in components as I psi. Let me call upper component even component and lower component odd component. So it will be time derivative of the spinor equals minus 0.11 psi odd minus I m minus psi naught. All right, so this is the Dirac equation in components. Yes. The Fij. Yeah. Oh, because we in 1+1 dimension. There's it's 0. I went back to 1+1, so it's just I is 1. So I goes from 1 to 1. All right, so this is the Dirac equation in components. And now the idea by Kokot and Susskind is to put them on a lattice. We have to introduce staggered fermions, which means basically that we put on the lattice fermions and we distinguish even sides of the lattice and odd sides of the lattice. So let me show what it means. So I would like to reproduce this equation on a lattice in a difference form. So what I do is, okay, let me define the Hamiltonian. So I replace my field, my upper field psi e on the lattice side xi. I replace it by a fermion. Let me call it now ci. And this is only for even sides. And I replace my odd field on the lattice also by fermion. I'm going to call it this also ci, but now I goes odd sides. So now if I draw my lattice, so I have even and odd sides. Right. I just so far I would like to consider fermions only. Yeah. Just we will add gauge field slightly later. I think there are many ways to put them. There's a way to put them on one side. This is just a construction, I guess. I'm not sure. Maybe there's this fermion doubling problem or something like that. I'm not sure exactly, but I think this is a construction, which there are probably many ways to do this. But here you can see nature. Why you will see in a moment why it's kind of natural to do.
Which is the minimal number.
All right, so put this on the lattice with the distance a, and so let's say here it's even, here it's odd, it's even, it's odd, and say this is ci plus 1, ci minus 1. And so the physical distance between sides is a, so it's a lattice spacing. And now the Hamiltonian for the Dirac field in this formalism will be just minus I over 2a, sum over I, ci dagger, ci plus minus. So it's a similar Hamiltonian which we saw already for XY model. And now let's see how it works. So if I now would like to check this equation of motion for this Hamiltonian, so I'll write that I ck dot is a commutator ck with Hamiltonian. Oh, I forgot the mass term here. So there's also a mass term which is minus I m, and there's a sum over -1 to the power of I ci dagger ci. All right, so if I now would like to compute equations of motion for my operator C, which replace fermions, so I get that I ck dagger is minus I, and here I'll the first term will give me ck plus 1 minus ck minus 1 over 2a, and the mass term will give me minus plus I or minus I and minus 1k. So you can see here that what happens is that now you can see why the staggered fermion construction works, is that if I take an even side, so I take say k even, then I get here a difference on the odd sides, right? So it's going to be minus ck plus 1, which is an odd side, minus ck minus 1 over 2a. So these terms are now odd on odd sides, and plus m. So this gives me this Dirac equation. So if I put now even, I have here minus delta psi odd over delta x plus minus psi even. So yeah, so I exactly reproduce this Dirac equation for each component. So if I now do it for the odd component, I'll get minus delta psi even over dx minus m. So I here. All right. So that's how fermionic part works. Now let's add the gauge field. So sure.
In the left, you have the derivative of C. That, I guess, is something you're going to discretize as well.
This one.
No, the left. So you have the derivative.
Over time.
Yeah.
Yes.
Okay, that's over time.
Yeah, it's over. All right, so now we add a gauge field, and so we have to, as usual, if we have ci dagger ci plus 1, we have to replace it by ci, and there's a Wilson line integral over xi plus 1 of the gauge field A1 x ci plus 1. So you can write it as this u operator, which is e to the power of IE times A, the lattice spacing, gauge field at some coordinate xi. So if I have here xi plus 1. So my gauge field in this lattice formulation, it leaves on a lattice links. So this is essentially where my gauge field leaves, and this is and the fermions, they leave on the lattice sides. Right, so it's here. And let me just write it as I to the phi I. So now we know that the electric field, which is a canonical momenta, have a commutator with the gauge field, which in the discretized version will be minus I over A delta Kronecker ij. So when we put them on the lattice as well, so they're going to have this commutator, discretized commutator, and that means that my gauge field, my electric field, Xi, have a commutator with this link variable U is equal to just E times charge times Uj j plus 1. Which means that for my electric field, I can take representation, which is E of x I is E charge times operator Li, where Li is just minus d over d phi I. So it's my gauge field variables. Phi is basically E times A times capital A of xi. It's just a definition of the gauge field. Yes.
Relation between E and U, is it exact in N, or is it?
Yes, so E is actually derivative over A. So,
Zero order term, which gives me commutator of E with 1 is 1.
so I think E just is derivative over A, essentially.
The commutator, and expanding this in A. So U, the zero order expansion is just identity making, right? Because this is exponential.
Yes.
Commutator of E with identity, which should be 0, is equal to 1.
No, I think it is not.
The Li should be changed to Ln because there are too many i's.
Oh, I see. So this has to be. I think what I forgot is to put here delta ij. Yeah.
Here, in the box.
Ah. All right. Yeah, there are too many i's. All right, so that means that the first term, the first term, which is Coulomb energy term, which is E square, let me call it HC, which was integral over 1/2 E square. E can be replaced as a sum. So I'm going to have A, then E square over 2, sum over N, ln square. And the Hamiltonian for fermions is now minus I over 2a. So this minus plus right, so that
Hamiltonian for fermions by A also. Okay.
sorry.
Integral measure dx is multiplier the fermion Hamiltonian by A also.
Oh, you mean here? No, here it's already taken into account because it reproduces the equations. All right, so that's the Hamiltonian now on the lattice, and now let's see what's the Hilbert space of this quantum Hamiltonian. Right, I think I should start raising something. All right, so the Hilbert space at this moment, the Hilbert space of our Hamiltonian is spanned by vectors. Let's put it on the lattice of size n. So it's going to be n0, n1, and n-1. So it's a fermionic part, and the bosonic part, the gauge field part, will be this. Let me explain. Where all this ni, they either 0 or 1, and l, I, they any integer number. So the fermion state, when it acts on a vacuum, I is 0, or it creates a state. For bosonic variables Ln,
integers or the bosonic ones?
yeah, it can be negative as well. So it's Ln which acts on L, is going to be L n. So the phi's, they are raising operators. So if I act by phi on Ln, it will be L plus 1. If I act by minus 1. So it's a rotor, right? So it's the bosonic creation annihilation operators, and this is fermionic. Fermionic. So these are exactly the fermions which we saw in the first lecture, and now this is the bosonic field here, which represents the gauge field. And okay, we have our lattice. Let me write it again. So we have this staggered fermions, 0, 1, 2, 3. And we want to have even number of lattice fermions, because basically each fermion in the staggered construction it's represented by 2 sides, right? So that's the lattice. So at lattice sides, lattice sides, we have our fermions, C0, Ci, Ci plus 1. And at lattice links, we have our bosonic fields, L0, L1, here, Li. That's the construction. And but now we forgot to mention the very important part in this construction. Actually, so far I didn't mention the Gauss law. And the Gauss law, what happens in this one-dimensional model is that the Gauss law completely connects bosonic degrees of freedom with fermionic degrees of freedom. And this is the only special thing about the one plus one dimensional model. So the Gauss law is delta x equals psi. And if we'd like to put it on a lattice, so we replace this this derivative by e times Ln minus Ln minus 1. And this part, which is a charge, is E times Qn, where Qn is the charge on a site n. So the Gauss law tells us that basically, if I have a site n, here my Ln and here my Ln minus 1, that the outgoing electric field Ln minus incoming electric field Ln minus 1 equals charge of my site, Q. And but what is the charge here? And so now we have to define charge in such a way that we have to incorporate for positrons and electrons in this model. And one way to do this, and it was historically defined in the paper by Hamer in '97, is to basically declare that our charge is Cn dagger Cn. This part is natural, but then we have to subtract the delta Kronecker, which is n, comma O, which means that on even sides, we have charge which can be 0 or 1, and that corresponds to electrons. But on odd sides, our charge is -1 or 0, and this corresponds to positrons. All right, so this is the Gauss law. You mean which? It's not actually improvement. It's I think physically necessary term, because we would like to have sort of a Dirac sea, in the sense that we want to have positive charge particles in our system. So we'd like to have positrons. So if we want to have this term, then there's no way to have positive charge in the system at all. So in this construction, our ground state would be a half field construction, where we can then, when we apply fermions, we can have positive or negative excitations. Yes. it's some way, it's something we have to put by hand. Yeah. This somehow in the original paper by, there was a paper by Banks, Kogut, and Susskind in 76. They didn't mention the Gauss law. I don't think this is the only way to interpret. I don't think this is the only way to deal with it, but that's a way at least. Yeah. Yeah, from this equation, naively, you would get just C dagger C. Yeah, but then. This term. No, it doesn't matter because in continuum limit you do have positrons, right, in the system.
So what does it like in the continuum limit? Some total derivative.
In continuum limit, it looks like this, right?
A not term, that one.
Yeah, it maybe turned out to some normal order term like here, but then you know that physically, if you apply your psi field to the vacuum, you can generate positron. Right? That's the idea. But it's not the only surprise about the lattice construction, so I'll mention other things. All right, so in one plus one dimension, this Gauss law, it completely constrains bosonic degrees of freedom. Let me explain why. So I can try to resolve this equation. So I can write Ln equals Qn plus Ln minus 1. So it equals Qn plus Qn minus 1 plus Ln minus 2, right? So and then it's equals to essentially sum over k from 0 to n qk. So my electric field, which is in this case is natural. So if I have my sides here, and they have charges q0, q1, qk. So my outgoing electric field here, Ln, is a sum of all these charges, right? So if I total charge, which is on this side. And we also, in this construction, I also assume that I have 0 incoming electric field. So L minus 1 is set to 0. And also I'm going to assume that my outgoing electric field, which is at the side n minus 1, Ln minus 1 is also 0. So I don't have incoming electric field and I don't have outgoing electric field. And it gives me a constraint that my sum over all charges in my system, Qk, k equals 0, must be 0. So, which also natural, because if I don't have, if I have uncompensated charge in my system, I'm going to have outgoing electric field out of my lattice, right? So this is what I assume. So now, again, using this relation, using Gauss law, I can express all bosonic operators through fermionic one. So I can if I know fermionic configuration, that means I know my bosonic configuration. So that means that my Hilbert space, which consisted of product of fermionic degrees of freedom and bosonic degrees of freedom, now becomes purely fermionic. Now consists only from the fermionic degrees of freedom. So, and bosonic degrees of freedom, they follow essentially from my fermionic configuration, right? So where my filling numbers are either 0 or 1. Okay. So because of the Gauss law. So so this is the Gauss law. It tells me that outgoing electric field minus incoming electric field is the charge at the lattice side. So now I can solve it. So I can recursively apply this this formula, because it's one-dimensional formula, and then I can express any bosonic operator, my electric field operator Ln, through the sum over charges, which basically tells me that the electric field here is the sum of all charges on the left. And I can do this for all of the electric operators. Yeah, it's a particular choice. Yeah, we can add theta angle, meaning that we have some incoming. Yeah, but I'll try to be as simple as possible. So that's the natural thing. Is just we don't have anything outgoing. Yes. Yes. Exactly. All right. So finally coming to this lattice formulation. And so now we can use it, and we can finally write the Hamiltonian, the full Hamiltonian, in the following form. So it's going to be e square a over 2 sum over n from 0 to n minus 2. Now here sum over k from 0 to n cube k square. So there's going to be the electric Coulomb energy term minus a. And now in my fermionic part, what I can do, essentially, I can drop all of this phi e to the I phi terms, because essentially their role is to properly adjust the Hilbert space, bosonic Hilbert space from the fermionic Hilbert space. So I can write now this term as Cn plus 1 minus Cn. So I dropped this e to the I phi n coefficients, and finally I have here m. Now let me put m lattice sum over n from 0. Right, so this is now the Hamiltonian for the Schwinger model, which depends only on the fermionic degrees of freedom, Cn. Right, and here I put m lattice because what recently was discovered by Ross Dempsey, Igor Klebanov, Sylvie Pufu, and Bernardo Zahn, that in order to preserve some remnants of the chiral symmetry, you have to take lattice mass, which is not exactly m, which we started with, but we have to correct it by the term, which is 1 over 8 e squared times a. And this term disappears when a goes to 0. So if we go to continuum limit and we take lattice spacing smaller and smaller, this term disappears and m lattice goes to m. But when we do calculations, we have to, this term drastically improves the convergence. So, and in order to see that this term is there, you have to look carefully about symmetries of this Hamiltonian. You want to preserve as many symmetries as possible. And then they discovered that they had to add this term, and numerically, this term drastically improves the convergence of the calculations. All right, that's point. Yes. Yes.
Extremely non-local.
Exactly.
Now, if the question is, we could start with this continuum Hamiltonian, which I don't see on the board right now. Maybe on the top part, still there, and try to use the Gauss law constraint there to integrate out the electric field, and you would basically get a term of the form charge, absolute value of linear separation, another charge. Could discretize it then. My question is, would this procedure lead to the same Hamiltonian?
I can do it in my head. I don't know. Maybe it's maybe you can work it out as an exercise. I don't know.
Over something like this, like Qi, Qj times I minus j.
And basically, I'm not seeing naively if I had like a term Q, or actually J, because it's current, times current at some point X, then absolute value X minus Y, current at some point Y, which basically is linear potential between charges.
Yeah, exactly. It is a energy. It's a Coulomb energy term.
We discretize it as sum over positions and linear term. I don't see immediately how this sum over charges squared.
Yeah, I mean, the nice thing about it is, what I'm going to continue, is that whatever you do, whatever Hamiltonian you get, you can know when you test it numerically using density matrix normalization group, you can see whether you get physical, like the right answers, which we know from theory. So it's always a nice thing because you can check everything. All right, so you're right that's the most interesting term in this model, because these two terms, essentially this term is exactly the XY model term, which I considered last lecture, and this is just is just a mass term, which is just a diagonal on each side. So this term here, the Coulomb energy, is non-local, but nevertheless, it's still possible to apply the same procedure, the same density matrix normalization group procedure, which I discussed on the previous lecture. And essentially, we're going to focus on this term now. But before we do again, so in order to solve this system numerically, we have to go back to spin variables now. So we do again Jordan-Wigner transformation. Slightly different in this case. So now we basically say Cn equals product of k less than n minus sigma kz times sigma n minus and Cn Dagger plus sigma kz. Right. So we again do Wigner transformation, and for the Hamiltonian, we find that, okay, this is, let me put this term as a Coulomb term, and here we're going to find exactly, let me define normalized Hamiltonian, so H twiddle, which is 2H over E squared A, and this Coulomb term plus X sum over sigma n plus sigma n plus minus. So this is exactly the XY model term plus sum over minus 1n and z, where yeah, so that where x here is just 1 over e squared a squared, and u is this 2m lattice over e squared a. So now it's just a spin chain model, but essentially it's an XY model plus this Coulomb energy, which is the non-local term, non-local Coulomb energy. Oops. So it's a 1/4 sum that's sum over k. Right. So, and also on top of this, we have the constraint that we have open boundary conditions with 0 ingoing and outgoing field, which translates to condition that sum over all sigma z, which is total spin z in the system, is 0. All right. So now, again, just to repeat what I already said, the Schwinger model Hamiltonian in this formalism is essentially the sum of this non-local Coulomb energy term plus this local XY model terms. And XY term we already worked out last lecture, so and how to apply density matrix renormalization group for this term. But now we're gonna work out, and the rest of the time we're gonna see how we can work out this term. It's non-local, but then there's no obstacle to apply the same ideas to this term. Right. Right, so basically to see how to construct density matrix renormalization group, we have to analyze how we can build our chain step by step, or how we can build a chain of size n plus m. How we can build a Hamiltonian of size n plus m using Hamiltonian of size n, Hamiltonian of size m, and other operators, right? So that's the idea. That's the main idea. So if we have a chain part of size n, and we have a spin chain of size m, we need to analyze how to build an m chain, n plus m chain out of this two. And in this case, for this Hamiltonian, we will need two additional operators, just two additional operators. So one is a n, which is just sum over n from 0, n minus 1 sigma nz. And second operators we will need is b of n, which is sum minus 1 and minus n. Right. So in case of XY model, we need also sigma left plus and sigma plus and sigma minus operators. In this case, we need these two additional operators. So now having these operators, we can write the law how to grow this, how to build a, this non-local Hamiltonian for n plus m chain out of this n and m and these operators an and am, bn and bm. And in this case, this law looks kind of asymmetric. So one can check. It's basically just some exercise to check that this non-local Hamiltonian, for the case of n plus m, is Cn times identity of part m plus identity of part n times Cm. And now the terms which connect both sides are an times bm. And another term is m an plus 1/2. Right. So there's this simple but sort of asymmetric law to build the n plus m chain out of n and m chain. And that's everything we need to formulate the density matrix renormalization procedure. That means that now to apply it to this Coulomb term, we have to keep track of these three operators, H, A, and B. And also to do this, we have to formulate the law how to grow both A and B themselves. Right, so an plus m is it's very simple. It just an plus im, m. So A is completely local operator, but Bn is non-local, so it's going to be Bn. So HC and B, they are sort of non-local operators, and they have this asymmetric form of this law how to build a chain of n plus m from the chain n and m. But this is not a problem to formulate the procedure for that. So now basically to construct the density matrix renormalization group, what we have to do, we have to use this formulas how to build Hamiltonians and proceed as we did for XY model. So if we have a chain of k sides from the left, in this case, because we know that in this staggered fermion construction, the two sides represent one physical fermion, it makes sense to grow the chain by two sides each time. So we grow chain left chain or system part by two sides from the left, and we do the same for the right chain. So it's also k. So we grow left and right chains by 2 sides each time using this formulas for Coulomb energy and A and B operators. So here, essentially, we just need to apply this formula for k plus 2. Right? So, for example, if I want to grow it by 2 sides, I apply it for k plus 2. So it will be, let me call it left now, left bar k times 2 plus I k bar times 2 plus a left k times b 2 plus 2 So that's just one formula for growing the left block for Coulomb Hamiltonian. And the same formula you can write for A and B. A left k plus 2, B left k plus 2. And of course, I mean, we're not solving just a pure Coulomb field, but we have to solve the whole Hamiltonian. So we also need to do the same procedure for XY part, right? For the XY part. So that means that we totally have to keep track of 6 operators. So 3 operators for this Coulomb energy part, and also 3 operators for the XY part. So we do this from left to right, and we again construct the super block as we did last time, and look for energy and eigenstate. All right, so that's the procedure. And finally, let me mention that maybe the most simple thing to check in this case would be to compute the Schwinger mass. So in the massless case, in the massless Schwinger model case, so if in massless Schwinger model, the photon gets a mass, which is called Schwinger mass, which is m squared is e squared over pi. And that means that when we do this computation, so we have Hamiltonian h little, which is 2h e squared over a. So we can in that symmetric normalization group, we can compute the ground state and the ground energy of a system of, say, n sides, and we can compute first excited state. Then the difference between excited state and ground state energy of the Hamiltonian, it's going to be this mass, so e over square root of pi. But because we work with this normalized Hamiltonian h twiddle, that means that we can rewrite this as a E1 twiddle minus E0 twiddle n over 2 square root of x should approach, so this difference of energies should approach 1 over square root of pi if we take n large, the number of spin chain large, and also continuum limit taking lattice lattice spacing a to 0. So so basically h twiddle is the Hamiltonian which I wrote there. So just computing in DM or G the energy levels of ground energy in the first excited state, and then taking their difference in the massless case, meaning that, again, using prescription by Ross, Sylvie, Rieger, and Bernarda, we have to take lattice mass equals minus 1/4, minus 1/4. So that would correspond to the lattice massless case for the Schwinger model. We will see numerically quite easily that it does approach the Schwinger mass of a photon. So that's probably the most simple thing to check numerically, which you can do using my Mathematica file now. All right, so it came from this proper my normalization of the H twiddle. That's what I called H twiddle. It's 2/e²/a. So now the energies of H twiddle of the Hamiltonian, which I define on my lattice, are going to be E1 twiddle, E0 twiddle, and they are related to real energies by this factor. So x, remember what I defined by x was E²/a². So essentially, H twiddle is what? Yeah, is
It's not
2.
the position. I thought it was the position, but now I can
Yeah, x is just the coupling. Yeah, it's just electron charge times lattice spacing. So just a redefinition. But yeah, okay, let me stop here.
Yeah, thanks a lot for very clear lectures. Yes.
Deal with the Gauss law constraint, because you never talked about it. It mods out, but you threw out like part of your.
By the Gauss law constraint, you mean this one? That means that there's no incoming and outgoing field. You mean how do I deal with it numerically, or? It just means that when I diagonalize my Hamiltonian, in principle, I can have states which have non-zero total spin, but that's not my physical state. So I have to, well, first I can, one way, just a naive way, would just to compute all states and then see which states have spin 0, and the ground state has spin 0, spin as 0. The more correct way, smart way would be to optimize this procedure by projecting already, like doing this by projecting already on a spin 0 sector, which is a bit tricky, but it could be done.
When you enlarge, you can't. So, like if you threw away spin 0, you can't enlarge it. Enlarging the system, you spin 0, spin 1 times spin 1.
Yeah, you're right. I mean, to write the density matrix normalization procedure, keeping total spin 0 is some needs to some, it's possible to do, but it needs, you need to do some work to write a code which keeps track of all spin sectors and combines them to total spin 0. Yeah.
And the first excited state will also have spin 0?
The first excited state, in this case, we're gonna have spin 1. So really, to compute E1, that E1, you need, if you do it in a naive way, if you don't project on a spin 0, if you want to compute this energy 1, then you have to take a second excited state. Second excited state will give you this E1 in spin 0. Or if you do in a proper way, in a smart way, is just to project on a spin 0 from the beginning in your procedure, then the second state will be E1.
Is there any direct comparison between this Hamiltonian approach and the 2D lattice simulation by Monte Carlo? It has greater advantage in this model.
I don't know much about Monte Carlo, but I would say that this approach in 1+1 definitely has advantage over Monte Carlo.
Yeah, it's not only extremely precise, but it overcomes the doubling problem. Like this is really the formulation for one flavor. I believe like if you just do the basic staggered Euclidean thing, you'll get two flavors. But people do, I guess, use Wilson fermions. But this is, I think, the preferred way. It gives precision at what, 10 to the minus 5 for this quantity.
Well, the precision is up to you, basically. You can get the machine size precision here if you just if you keep the large enough number of states when you do truncation, then you can reach machine size precision. So it's very precise. So you can get this. I don't think Monte Carlo can do.
I guess you do need to extrapolate to infinite x. This a to 0 limit is like you do it for, but the convergence is fast, right?
Especially when if you take the proper mass using this prescription, then convergence is really fast. Yes.
Yeah.
So could you write down how does higher symmetry act from CI?
I guess I would refer you to the paper by.
Just a page to like page.
It just shift by lattice side, I think.
Yeah, just shift by one lattice side. In this particular case, you also need to shift theta to pi, from 0 to pi. But actually, in my lecture, I'll mention the two flavor model where it's just literally just shift by one side.
Yes, this Hamiltonian formulation, how do you control the lattice spacing?
I guess, you mean through these parameters, x and mu. So the lattice spacing which goes to 0 means that x goes to infinity.
It's the charge.
Yeah, and then you take x bigger and bigger. But already for x around like 50, it's the convergence to continuum is very good.
You not need to find the relation between like k and the coupling of the model and Lagrange formulation with the beta function. There is more.
I think here it's 1 + 1 series, so you don't need to put
this. More questions? Yes.
So is there any way in which you can see that this form for the Hamiltonian is the only thing that obeys like Gauss's law for the bigger spin chain?
No, I think it's the a version. So I think there are different formulations for the lattice model. Yeah, there are. It's not the only one.
Did you have?
Can you also put the model on a chain with periodic boundary conditions?
Yes, you can. But then, first of all, for periodic boundary conditions, if you want to apply density matrix normalization group, it will cost more. But plus, in this case, you will need to keep track of the bosonic. There will be one bosonic degrees of freedom of like circulating electric field over the circle, and that you have to basically deal with it because each bosonic degrees of freedom is infinite in the beginning, right? So it can be L. In my case, can be from -infinity to +infinity, so it's integer numbers. So to deal with it, you have to truncate it. If you want to formulate density matrix normalization group, you have to truncate it. But then people did it, and yes, I mean the short answer is yes, you can do this.
How is this related to the problem of confinement? Is the idea to extend that to higher dimensions?
Yes, I think the challenge is to at least put it to 2 + 1. And people already trying to do this. It's much harder because Hilbert space, Hilbert space grows very fast once you go to 2 + 1. But there are few attempts already made in this direction. But at least this method can help us to fully explore all 1 + 1 dimensional field series, I guess.
If this can be done with similar precision in 2 + 1, that would be a big breakthrough. All right, let's thank Grisha again.